Hello everyone. Today we will try to solve some problems from the topics that we have discussed in my last lecture on linear vector space. Here is the first problem. Two ket vectors are given from the vector space that consists of matrix as vector elements. Two ket vectors are given, psi and phi. So in the first question, we have to find the bra vector that corresponds to the given ket vector of phi. And then in the second question, we have to find the scalar product of these two vector. Given two vector, we have to find the scalar product. And then we have to check whether the complex conjugate, taking complex conjugate of this vector is same as bra vector or not. Okay. So let's find the answer for the first question. We know from quantum mechanics that ket vectors are elements of Hilbert space. So ket vector, elements of ket vector, the vector that we are representing as ket are elements of the Hilbert space, and then bra vectors are elements of the dual of Hilbert space. So these ket vectors, if the vector space elements are matrix, then these ket vectors will be denoted as a column matrix. And if the elements of Hilbert space are matrix, then the bra vector are nothing but a row matrix. Okay, and then this inner product between two vector psi, phi and psi is the product of row matrix and then column matrix. This will give us a constant, complex constant in general. Okay, so the given ket vector phi is 2 minus I, 2 minus 3i. Okay, ket phi is 2 minus I, 2 minus 3i. Okay, what is the corresponding bra vector? So we have to take complex conjugate for each elements of the matrix, and then if the ket vector is row matrix, then column bra vector will be a if the ket vectors are column matrix, bra vector will be a row matrix. So take the complex conjugate and convert this as a row matrix. So it will be 2i, 2 plus 3i. This is equal to the bra phi. Okay, this is the answer. So our bra phi is 2i, 2 plus 3i. Okay, now second question, evaluate the inner product of phi with psi. Okay, so what is the scalar product of phi with psi? So we have to put, at first we have to write the bra phi, which we have already found in the first question A, that is 2i, 2 plus 3i, and then the ket psi. Ket psi is minus 3i, 2 plus I, 4. Minus 3i, 2 plus I, 4. Now what is the multiplication of these two? Minus 6i plus 2i minus 1 plus 8 plus 12i. So these two term will give you 4 minus 4i, and then adding with 12i we will get 8i plus 7. Okay, this is the scalar product of phi with psi. So scalar product of phi with psi is 7 plus 8i. Okay, this is the answer. Now coming to the third question, is phi star and bra phi are same? Let me check. See, So what is 5 star? 5 star is, so just we have to take, we should not change it column matrix as row matrix. Just take the complex conjugate for each of the elements of 5. That will be simply 2i 2 plus 3i. Okay, this is 5 star. Whereas bra 5 is a row matrix which consists of the elements 2i 2 plus 3i. Here you can notice immediately that although elements are same, but 5 star is a column matrix whereas bra 5 is a row matrix. These two are completely different and they are not equal. Okay, that's all the first question. In the second problem, two ket vectors are given, ket psi, ket phi, and they are given as a linear superposition of two orthonormal vectors phi 1, phi 2, phi 1, phi 2. Okay, now we have to calculate the addition of these two vectors in the ket space and in the bra space. Also, we have to find the inner product of psi with chi and chi with psi. And in the third question, we have to verify that these two vectors, given vectors, will satisfy Schwarz inequality and triangle inequality or not. Okay, let's try to first we'll try to find the bra vector for the given two ket vectors. Ket psi is given, ket chi is equal to minus phi 1 plus 2i times phi 2. Okay, so since two ket vectors are given, straight away we can add for finding the addition of these two vectors in the Hilbert's in the ket space. Okay, answer for the first question, directly we can add psi plus chi is equal to how much? Minus 1 plus 3i times phi 1 minus 7i plus 2i. So it is minus 5 times I into phi 2. Okay, now we have to find the addition of these two vectors in the bra space. Since bra vectors are not given, at first we have to find the bra vectors for these two ket vectors, and then we have to add straight away. We cannot add any bra vector with ket vector because they are coming from two different space. We cannot add, so we have to convert them as first bra psi. So what it will be? So we have to take complex conjugate for this element, and then this ket phi 1 will become as a bra phi 1, and this become 7i times phi 2. Okay, here the ket chi will become as minus phi 1 minus 2i times phi 2. Okay, now we can add them to find the addition of these two vectors in the bra space. Sorry, here it will be chi. Okay, this will be, now what will be the addition? Minus 1 minus 3i times phi 1, 7i minus 2i, so it is 5i times phi 2. So this is my addition of this vector in the bra space, and this is in the ket space. Here you can see what is the difference between these two vector, addition of these two vector in the bra and ket space. You can see this is nothing but complex conjugate of this, and here minus 5i it is plus I. So it's equivalent to finding the, for elements we have to take the complex conjugate and get vectors, base vector will become Bragg base vector. That is the difference. Now we will try to find the inner product of psi with chi and chi with psi. Okay, now what is the inner product of psi with chi? First, what is bra psi? Bra psi is given, which is minus 3i times phi 1 plus 7i times phi 2 multiply with what? It is gets chi. So which is minus phi 1 we know. So to compute this term we need to use the orthonormal properties of base vector. So if we have base vector, if you take inner product between these two, you will get Dirac delta function here, Kronecker delta. So whenever I is equal to j, you will get 1, otherwise it is 0, because they are orthonormal vector. So here the cross term will get vanished. Only the surviving terms are only this. Whenever you are multiplying the like term, you will get some value, otherwise you will get a 0 value. Okay, so use the orthonormal properties right away. So what you get here, minus 3i, here minus 1, so it is plus 3i, and then here 7i, here 2i. So I squared, we know iota squared is minus 1, so minus 14 times phi 2 inner product with phi 1. We know these two are base vector and they are normalized vector. This will give you 1, so it is 3i minus 14. So answer is, since it is a inner product, here you can see your result is just a complex number, a constant, minus 14 times plus 3i, just a constant. Okay, now we will find inner product of chi with psi. What is Bragg chi? Bragg chi is given here as here, minus phi 1 minus 2i times phi 2 minus phi 1 minus 2i times phi 2 multiply with what? Get psi. Get psi is 3i times phi 1 minus 7i times phi 2. 3i times phi 1 minus 7i times phi 2. Okay. Now what is the inner product of these two vectors? So here you can see minus 1, 3i. So it is minus 3i times phi 1 product with phi 1 and minus 2i. So it is minus 14 times I. So phi 2, phi 2. So we know inner product of this like base vectors is 1. So it is minus 14 times minus 3i. So this is the answer. Here one important thing you can notice, that the scalar product of psi with chi is not equal to scalar product of chi with psi. You can notice from these two equation, let's say 1 and 2. Here you see scalar product of psi with chi is 3i times minus 14 and chi with psi is minus 14 to minus. In fact, it is complex conjugate to each other. So we can write here that scalar product of psi with chi is equal to scalar product of chi with psi and then taking complex conjugate. Okay. Now coming to the third sub question, whether psi and chi satisfy Schwarz and triangle inequality or not. Okay, let me write first what is Schwarz inequality. The any two state vector from the Hilbert space will satisfy the Schwarz inequality, which says that the mod square of inner product of psi with chi is always less than or equal to the product of inner product of psi with psi, inner product of chi with chi. Okay, this inequality, if vectors are linearly independent, then this inequality must hold, otherwise it will not hold. Let us check for the given two vectors whether this inequality is satisfied or not. Okay, what is the given psi and chi vector? Okay, I have to write it again. So 3i minus 7i. Let me write, say 3i minus 7i time, and then minus 1 2i minus 1 time plus 2i time by 2. Okay, now take the scalar product of this chi with psi with chi. What will be the scalar product of psi with chi? We already found what it is psi with chi. You can notice here this is the scalar product of psi with chi. So we have to take the mod square of that. What it will be? Minus 14 plus 3i. Okay, let us take the mod square of that. Minus scalar product of psi with chi is minus 14 times plus 3i. Correct? Yes. Okay. Now how to take the mod square of this? It will be this into complex conjugate of this, minus 14 times minus 3i, so which will give you 196 I think. So it will be 196. So and then this will be 3i the whole squared, so there will be a minus 3 minus this will be, so 9 plus 9, how much it will be? 205. So this is the scalar product of psi with chi and its square. Okay, now we know. Next, what is the scalar product of psi with psi and scalar product of chi with psi? We can immediately find the scalar product of psi with psi will be minus 3i times phi 1 plus 7i times phi 2 3i1 I times phi 1 minus 7i times phi 2. Okay, how much it will be? It is minus 9 plus 9, 9 plus 1, 49. So this comes about 58. Okay. Now what is the scalar product of chi with chi? Which will be, so you can easily write it minus 1 plus 4. I think it will be less only. So it will be 1 plus 4, 5. Okay. Now what is the multiplication of these two? So our right hand side will be psi with psi, chi with chi, which is 58 times 5. So 5, 8, 40, 4, 29, 290. Okay, my right hand side is 290, whereas my left hand side is here. LHS is here, which is 205. So my LHS is equal to 205. So 205 is always less than or equal to 290. Hence sparse inequality holds. So this is valid for the two given state vector. They are linearly independent. Okay. Now let's check the triangle inequality, which reads ABCD triangle inequality. Triangle inequality reads the inner product of addition of these two vectors psi plus chi is always less than or equal to the length of one side of the triangle psi plus the length of other side, which will be given by scalar product of chi with chi. So this equality, if vectors are linearly independent, then this inequality should hold. So what is the scalar product of psi with addition of these two vectors? Inner product of addition of these two vectors. Did we find what is the addition of these two vectors? Yes, we found it is. What is the addition of these two vectors? Here you can see minus 1 minus 3i 5i, minus 1 plus 3i minus 5i. Okay, let's take that minus 1 minus 3i plus 5i. So bra psi is equal to, first we will find this, what it is. My bra vector is, addition of these two bra vector is minus 1 minus 3i minus 1 minus 3i 51 plus 5i. And then sorry, it's a bra vector. Okay, bra vector, and then no, let me, there is a confusion. Minus 1 minus 3i 51 plus 5i times 52 multiply with this one. So it will be just a complex conjugate of this, minus 1 plus 3i times phi 1 plus, sorry, here it will be minus 5i times phi 2. So what is the multiplication of these two? This is my LHS, which will be this will be 1 plus 9, 10 plus 25, which is 35. Now what is the scalar product of psi with psi? Scalar product of psi with psi is 58. Scalar product of chi with psi is 5. 58. So on the right hand side we have square root of scalar product of psi with psi plus square root of scalar product of chi with chi, square root of 58 plus root of 5. So how much it will be? It will be around, I think on the, okay, straight away we can put here on the left hand side square root of 35, and the right hand side we have square root of 58 plus square root of 5. So I think this will be roughly 7. Square root of, what is square root of 35? It will be roughly 25, 6. Okay, close to 5.9 something, which will be always less than or equal to, we know square root of 5 is 2.226, 256 something, and then square root of 58 will be more than 7. So let me take 7.2. It's clear that left hand side is always is less than right, always less than right hand side, not always. Okay, for this case left hand side is less than right hand side. Okay, hence the triangle inequality holds. In the third problem, two ket vectors are given, psi 1 and psi 2, as a linear superposition of four orthonormal vectors phi 1, phi 2, phi 3, phi 4. Here you can see second vector also is given as linear superposition of four orthonormal base vectors phi 1, phi 2, phi 3, phi 4. Okay, if you see in the first vector psi 1, there is one unknown constant alpha, and in this question our aim is to find the value of the alpha so that psi 1 and psi 2 will be orthogonal to each other. Okay, let's find. Solution is, so we know if two state vectors are orthogonal to each other, their scalar product should yield 0. There is no projection of one vector onto the other vector. Psi 1, psi 2, the scalar product will be 0. Using this orthogonality condition, we are going to find the value of this alpha. Okay, what is bra psi 1? Bra psi 1 will be bra psi 1, let me write here. Bra psi 1 minus 2i times bra phi 1 plus bra phi 2 minus alpha times phi 3 plus 4 times phi 4. Okay, what is ket psi 2? It is 3 times ket phi 1 I times ket phi 2 plus 5 times ket phi 3 minus ket phi 4. Okay, Now what is the multiplication of these two? This is the scalar product of psi1 psi2, so which will be minus 2i times. So we have to use this orthonormality condition that phi I phi j is equal to delta ij if the base vectors are orthonormal. This is orthonormal. Okay, then this condition should valid. So minus 2i times 3, so minus 6i plus 1 minus I here, minus I minus alpha plus 5, so it is 5 alpha 4 times minus 1, so minus 4, that will be equal to 0. To implement this condition, this will be equal to 0. Okay, now when this will be equal to 0, here we have minus 7i plus 5 alpha minus 4 is equal to 0. 5 alpha is equal to 4 plus 7i, alpha is equal to 4 plus 7i by 5. This is the answer. Here a group of vectors are given. In the fourth question, a group of vectors are given A, B and C. Okay, they are the vectors from 3D Euclidean space itself, and we have to find them whether they are linearly independent or dependent set of vectors. So the theory of for this we need to have the idea of linearly independent and independence and dependence of vectors, group of vectors. So in my first lecture I have discussed the theory of that extensively. If you have not seen that, please have a look at first and then come here. So okay, let's try to solve this problem. If for a group of vectors to be linearly independent, the solutions of this equation, we have to frame an equation of this type: sum over ai times phi I of this equation. We have to frame such equation. I is equal to 1 to 3 in this case. Here this I phi I is nothing but this vector a, b and c, and ai some constant. Let's expand this. A1 times, I have in the first question I have three vectors a, b, c. So a1 times a, a2 times b vector plus a3 times c vector. So remember here that a vector means this has the components from real Euclidean space. We can represent them this way also: 3i plus 0 times j and 0 times k. So it has component along only in the x direction. Similarly, b vector 0 times I vector minus 2 times j vector plus 0 times k vector. Okay, and c vector also we can represent this way: 0 times I vector, 0 times j vector minus 1 times k vector. Now put that these vectors into this equation number 2, and so you see in a vector only we have a component, so we can write straight away this is 3 times a1, and if you put b vector in this equation 2, what you will get? You get minus 2 times a2, and if you put c vector in equation 2, you will get minus a3, that is equal to 0. Okay, when this equation will be satisfied? Oh, I forgot to put I, j, k unit vectors. I, j, k. You see these unit vectors are linearly independent set of vectors. Ijk are linearly independent base vectors basically. So these base vectors are linearly independent. By no way you can add these two. So the only possible solution for this equation is a1, a2, a3. So only possible solution is all the components are 0. That means they are linearly independent. So if the solutions of this equation 1 turns out to be all the ai's are 0, then this vector set that you consider is linearly independent set of vectors. As from this discussion we know the given set of vector in the question sub question A, all the vectors are linearly independent to each other. Linearly independent set of vectors. Okay, let's check this condition for the second case. Second question B. Here you have 6 minus 9, only two vectors are given, 6 minus 9 minus 2 3. 6 minus 9 0 minus 2 3 0. Okay, so frame such equation like we formed in the first question. A1 times A vector, A2 times B vector, this has to be equal to 0. So if you do this, what you get? A1 times 6i minus 9j cap j cap plus A2 times minus 2i plus 3j cap is equal to 0. So if you add this, what you get? 6a1 minus 2a2 times I vector minus 9. Okay, let me put minus 9 times a1 plus 3 times a2 into j vector is equal to 0. Oh, okay. Now you see when this will be equal to 0, whenever your 6a1, so it's like on the right hand side you can equate this way, 0 times I and 0 times j. So each component will be, when this will be equal to 0, minus 2a2 times 0. So this will 6a1 is equal to 2a2 and a1 is equal to a2 times 3, and here minus 9 times a1 is equal to minus 3 times a2 and a1 is equal to a2 by 3. So here you can see that they are not linearly independent. Here you can see a1 is equal to a2 times by 3, a2 divided by 3. So this set of vectors a and b are not linearly independent set. They are dependent set. Linearly dependent. Let's check this condition for the third vector. This one. Your a vector and b vector and c vector. Two 3 minus 1 0 1 2. 2 3 minus 1 0 1 2, and then 0, 0, minus 5. 0, 0. Okay. So frame the similar kind of equation. A1 times A, A2 times B, A3 times C is equal to 0. So you get A1 times 2I plus 3J minus K plus A2 times J plus 2K plus A3 times minus 5K is equal to 0. So you get A1 as 2A1 is equal to 0 and 3A1 plus A2 is equal to 0 and then minus A1 plus 2A2 minus 5A3 is equal to 0. Here you can see A1 is equal to 0. Since A1 is equal to 0, A2 from this equation is also 0. A1 and A2 is 0. From this equation one can say A3 also is equal to 0. Since all the components means all the coefficients are equal to 0, they are linearly independent set of vectors. Linearly independent set of vectors. That's all. Thank you.